The next reaction that dienes undergo that we're going to learn is very different from what you've seen before. It's called the Diels-Alder reaction. So the Diels-Alder reaction is an addition reaction. We don't lose any atoms. It occurs between a conjugated diene and a dienophile, which is often an alkene. It can also be an alkyne. And so one unique thing about this reaction is its mechanism. So instead of having multiple steps, this reaction occurs all at once, and the arrows sort of travel in a circle. So here we're starting with 3 pi bonds, 1, 2, 3, and all 3 pi bonds break in this Diels-Alder reaction. This Diels-Alder reaction is initiated by heat. That's what this triangle is. So that's another important thing here. And so when we heat up these 2 molecules together, what's going to happen in terms of the mechanism is that all of our pi bonds are going to break and form new bonds. So here what we're going to do is form a new sigma bond between this atom and this atom. This pi bond is going to shift over, but is going to stay a pi bond. This pi bond is going to form a new sigma bond between this atom and the other alkene. And so we've formed a 6-membered ring. And if we want to follow each individual carbon, let's start by following the alkene. Those 2 carbons are labeled in green. That breaks its pi bond to make just a sigma bond and have 2 new sigma bonds to our dienophile. If we follow our diene, it's obviously made those same 2 sigma bonds highlighted in green, but it's also has a new pi bond here. If we label these carbons 1, 2, 3, 4, in our starting material, we had double bonds between carbons 1 and 2 and 3 and 4. In the product, we have it between 2 and 3. If we look at the enthalpy and entropy of this reaction, in terms of entropy, this reaction is unfavorable because we're putting 2 molecules together. But because we're breaking pi bonds and replacing them with sigma bonds, it's a very enthalpically favored reaction. Let's look at an example. So the first thing we want to do is identify our diene and dienophile. So here, this is our diene. Our dienophile can either be an alkene or an alkyne. Here it's an alkene. So what's going to happen here is that this pi bond from the dienophile is going to make a new bond with, let's call this carbon 1, on our diene. Remember, this diene is symmetrical, so it doesn't matter which carbon is carbon 1. Of the 2 ends, you get the same molecule. This pi bond moves over, and this other pi bond between carbons 3 and 4 is used to make a second new bond. So if we call these 5 and 6, we're making 2 new sigma bonds, one between 6 and 1, one between 4 and 5. So in our 6-membered ring, if we label these atoms 1, 2, 3, 4, 5, 6, we've made 2 new sigma bonds. We've also moved our pi bond to be between carbons 2 and 3. We want to make sure we have all of our spinach on here, our extra functional groups. So we have a methyl group on 2 and 3. We have an aldehyde on carbon 6. We want to make sure we include all that. We are not worrying about stereochemistry yet, just the connectivity. So hopefully this makes sense. So now let's talk about factors that increase the rate of Diels-Alder reactions. So one thing that's a requirement is the diene has to be in the S-cis conformation. So if it's in the S-trans conformation, the reaction will not occur. So if you have a diene like this, so I'm drawing one that's in the S-trans conformation, you need to rotate it so it's in the S-cis conformation in order to actually have it undergo a Diels-Alder reaction. So here, both of our double bonds are in the trans stereochemistry, so we want that to be true here also. So this is how I'm going to draw this. So you need to do that before reacting it. This also makes it much easier to draw the products because this already looks like part of a 6-membered ring. But what can happen here is that sometimes if your diene is part of a ring, the diene is stuck in either the S-cis or S-trans conformation. So as an example, the most common thing you'll see that's stuck in the S-cis conformation is something like this. So this is always in the S-cis conformation. It can't rotate out of that because that would mean breaking the ring. So this is going to react faster than our initial diene. because it doesn't need to rotate, already in the S-cis conformation. So this reacts faster. On the other hand, if we're stuck in the S-trans conformation, so the example that your book shows is something that looks like this. This is stuck again because of the ring in the S-trans conformation. This means that it doesn't react at all. So this will never do a Diels-Alder reaction. Our diene that is not a ring, that's in the middle. It reacts faster than the S-trans, slower than the S-cis ring, the cyclopentadiene ring. The second factor here is going to be electronics, and this is going to most often affect the dienophile, at least in this class. So for the dienophile, what we want is for that dienophile to have electron withdrawing groups. So an example would be maybe something like this. We see that the alkene is directly attached to a carbonyl. That's an electron withdrawing group. So that would react faster than just simple ethylene. If we wanted to make this react even faster, we'd add a second electron withdrawing group. Let's add a different one this time. So let's add a ketone. So we're adding a ketone to both sides. This reacts faster. So electron withdrawing groups make our dienophile react faster. So one possible question I might ask is I might give you, these three dienes, these three dienophiles, and ask you which would be most likely to give you the fastest possible Diels-Alder reaction. So you'd look for the one that's forced to be in the S-cis conformation. You'd look for the one with multiple electron withdrawing groups. Those together would give a very fast Diels-Alder reaction.